Well, happy Easter and good afternoon. I know we said after the last video that we were just about done talking about estimation, but there's a couple other things we can say about estimation that would be certainly worthwhile. How big should the sample be if we're going to estimate something? Now, is that a meaningful question? Well, of course, it turns out it is, because, let me get back over here, because we've got three things going on here. We have a confidence. How confident are we in our estimate? And that's 1 minus alpha. And we can set that wherever we want. But we also have a margin of error, or a maximum error of the estimate. And those two words mean the same thing. And the symbol is E, and that's defined as T, alpha by 2, degrees of freedom, of course, and then S over the square root of n, where S would be the sample standard deviation. So we've got how precise our estimate is and how much confidence we have in that estimate. Now notice that n appears in E. And if we made n bigger, then the square root of n would be bigger, and so this ratio would get smaller. T alpha by 2, once we set alpha, T alpha by 2 is a constant. So if I've got a constant here and I'm measuring by a quantity that I can make smaller by just picking a bigger n, the net effect of that would be to have a more precise estimate. That is, E would become smaller. E is the margin of error. I would have less margin of error. So we've got three things that are interplaying here. We've got the margin of error, which I'll call E. We've got the confidence, which we are calling 1 minus alpha. And we've got the sample size, which we'll call n. But these things don't work in isolation. They play off of each other. And let me draw this last little curvy arrow, and I'll tell you what I mean by that. First of all, the diagram with the curvy arrows means that E is related to 1 minus alpha, 1 minus alpha is related to n is related to E. And the bad news is we can't simultaneously optimize all three. Now, what would optimize be? Well, 1 minus alpha, as big as we can make it. That is lots of confidence in what we're going to say is the probable value of mu. Lots of confidence, big 1 minus alpha. E, very small. I'd like to have as small a margin of error as I can have. And n, well, n is the sample size. And the bigger n, in one sense, the bigger n the better, but in another sense, bigger n means taking our sample will take longer and be more costly. So if I could keep n small, make 1 minus alpha large, and E small, that would be simultaneously optimizing all three of these. I can't do it. I'll optimize two of them and pay for it with the third one. Now, let's work through an example, and suppose that we wanted to estimate the mean mu weight of watermelons. I love watermelon. We've got a field of watermelons. Suppose we know they're black diamond watermelons, and we want to know when we harvest these what the average weight of black diamond watermelons would be when they're mature, and I think that's between 90 and 100 days. So how are we going to find that? Well, the key is to use E. Now suppose that we want to be 90, does it really matter? Let's just say 98% confident in the estimate that we give. So 98% would be 1 minus alpha, and that means that alpha by 2 would equal 0.01. And suppose that we want to have a margin of error that's no more than a half a pound, no more than 0.5 pound, then let's get started here on figuring out how big a sample would have to be in order to achieve these two goals. Well, we know that E is equal to T alpha by 2 S over the square root of n. So we can solve this equation for n if I would multiply both sides by square root of n over E, multiply by the square root of n over E, then this equation becomes square root of n is equal to T alpha by 2, and of course there's the degrees of freedom there. I'm going to write it this time. And S, now when I multiply by square root of n over E, the square root of n's cancel out over here, but I'm left with in the denominator the value of E. And now if we'd square both sides, we'd have n is equal to T. Usually we write degrees of freedom first. As long as you understand, I don't think it matters. And an S and an E down here, and we would have to square that. Now the other thing we would have to do when we calculate all of this, it may have a decimal part to it. Well, n is our sample size, and that can't have a decimal part to it. So we would just round this value up to the nearest integer, to the nearest whole number, and that, these two little brackets here, that's called the ceiling function, and it just means whatever's inside there rounded up to the next integer. So, oh boy, it looks like we're doing really some hotshot work here. We've got n figured out already, except not quite. Now why not quite? Well, not quite because you see in this T factor, we've got degrees of freedom, and the degrees of freedom is n minus 1. So if we don't know n, we don't know the degrees of freedom. There's a problem. Now S is the sample standard deviation. We compute that from a sample. But what we're trying to determine is how big should our sample be. We haven't taken a sample yet, and so we don't have a value for S. So E, I do know. We want E to be 0.5 pounds. So we're okay on E, but these two are held up by a lack of knowledge of N. So what are we going to do about that? Well, it's a two-step process. Number one, we recall that T, degrees of freedom, alpha by 2, is similar to almost Z, alpha by 2. Remember, there's not a whole lot of difference between T and Z. All right, there's some difference, but we're going to compromise now because I can't calculate T without knowing the degrees of freedom, but I know that I can approximate it with the Z. The other thing I've got in this equation that I don't know is S. What to do about S? S is equal to what? Well, here we go through historical records, we Google what the S might be, or if all else fails, we take a sample, a small sample, a preliminary sample, maybe of 10 melons, and we calculate S based on that small sample, the preliminary sample, and we use that as our value of S. And so we use past values, or a preliminary sample. Just a small preliminary sample. And that will give us a value of S that we can plug in right here. Now what do we have? Now we've got N is equal to Z alpha by 2 S from our preliminary sample over E, and we would have values to plug in for all of those, and we plug those in, do the arithmetic, square it, and we know how big n is. Now, in this problem, estimating the watermelons, we know that we wanted E to be equal to no more than 0.5, so I'll take the boundary 0.5. We know that our alpha by 2 is equal to 0.01, so Z alpha by 2 is equal to, remember how we get that? It looks like my calculator disappeared, but I will have to just give it to you. You know how to look these up. I wanted to do it for you, but my calculator I'd have to look for now. It's 2.326. Okay, here's just a short insert that I'm sticking in after I've made the other video, just to show you about finding Z alpha by 2. And you've seen this done before, and you've done it yourself several times, but let's look again at how we do it. We would say calculate probability distribution, and we would want, this is a normal distribution. Z, remember, is a normal distribution. So we would want a normal distribution, and we would want, what are we doing? We're looking for a critical value, so this would be the inverse cumulative distribution, so we select inverse. The mean is 0 and the standard deviation is 1. Now the area, let's use an input constant. The area to the left is what your calculators and what Minitab uses when they compute an inverse value. So we want Z alpha by 2, where alpha by 2 is 0.01. That means 0.1 to the right, which of course would mean 0.99 to the left. And so let's put in a 0.99 for our input constant, and that's all there is to it. We'll just say OK, and Minitab comes back with the 2.32635, and recall that's exactly the number that we got when we just relied upon what I had looked up earlier. Actually, earlier I had done it with a TI-84 calculator. This time we've done it with Minitab. So that's how we find the critical values in the area under curves. And we did a preliminary survey, small sample survey. I'm making this up, but suppose we did that and we found that E was, or S was 5 pounds. Then I think we've got everything we need to determine N. And we would say N is equal to Z alpha by 2. That would be 2.326 times 5. That would be S divided by E, 0.5. And then that result, we've got a square. And that's equal to, of course I did this earlier, it's equal to 541.027. And the convention is to use the ceiling function, so I would want to round that up. Ceiling function there, and this would be equal to 542 would be our sample size. So that's how we solve for sample size when we know the maximum error of the estimate, also called the margin of error. And we go out and we shop around for a value to use, at least temporarily, for S. So I hope you'll find this helpful. There will be problems similar to this assigned. You have a good evening.